So there are a few concepts that I needed to go over in chapter one, which is also linked to your next upcoming homework, which is homework five, circuit elements. Okay. So circuit elements in electrical engineering, we broadly classify into two categories. Okay, two categories, broad classification. And I've dropped this one too many times. Oh, it still works. And the two categories are source and load. A source and a load. Okay. So a source, again, self-evident by its very name, is supplying something, is providing something, right? It's a source for something. So in electrical engineering, a source is something that supplies energy. A load is something that consumes energy. Okay, load is something that consumes energy. A source always supplies energy. Uh, supplies energy, and a load is something that consumes energy. Okay, consumes energy. Now, um, for the most part, the components that we look at in this class are just the three components that we talked about, basically resistors, capacitors, and inductors. So resistors, capacitors, and inductors, right? Capacitors, resistors, capacitors, inductors. Now, capacitors and inductors, in addition to receiving energy, are also energy storage devices. So they store energy for just a short fraction of time, and they release it back into the circuit when needed. Now, that happens very, very quickly. Sometimes it happens in milliseconds, other times it happens in microseconds or nanoseconds, like very, very quickly. Okay, like there's be a discharge and then done, right? And there are real life applications for that. Right? There are real life applications for that. One of the applications would be the camera flash, right? You have your battery that is charging up. You might hear some whirring sounds. It's basically charging up a capacitor. Then it just instantly all of that energy is released all at once. So you have a blinding flash light, right? That's one of the applications. Anyway, source which supplies energy, meaning it supplies either voltage or current. And in real life, of course, you cannot have voltage without current. You cannot have current without voltage. But there are further classification. We say it's a voltage source, or we say we have a current source. So further classification of a source is as a voltage source or a current source. Now in real life, as I said, the device that's supplying energy, the power supply unit, the PSU, is exactly the same device. It's exactly the same box. There's no difference whatsoever. You cannot have voltage without current. You cannot have current without voltage. And so they're one and the same thing. So then what's the difference? Well, a voltage source supplies a fixed amount of voltage while varying the current. And a current source will supply a fixed amount of current while varying the voltage. And I will explain how that works. So here, the output is fixed voltage and current varies. Here, the current is fixed and the voltage varies. Okay, the voltage varies, and I will explain how that works. The symbol for a source is a circle. Okay, the symbol for a source is a circle. So you would already seen this in the textbooks and physics classes, right? It's a circle. A circle with two terminals. A voltage source is noted, a voltage has polarity, plus and minus. So voltage source is noted by having a plus and a minus sign inside the circle. So if you have a plus and minus sign inside the circle, then it's a voltage source. If you have a arrow inside a circle, the arrow is noting that there's a current, right? Current flows through, so it's noted always by an arrow. So an arrow inside a circle signifies or notes that it's a current source. Okay. Make sense? Right? So now, as I said, in real life, the device is one and the same thing. There's no difference. It's supplying voltage, it's supplying current. The only thing is it changes and it varies. And so here's the important point. When you actually look at a real life power supply, like a benchtop power supply, it will have mode of operation. The mode of operation is known as constant voltage mode or constant current mode. So if you look at a power supply, it will have CV and CC somewhere in the settings. And so in real life power supplies, you run it as a constant voltage mode, CV mode, and constant current, CC mode. Okay. So if you have taken E251 and you've already done the lab in room 126, the power supplies that we use, there'll be a tiny CV next to the current on the right side of the display. If you ever see CC, then you want to let your professor know how to change it. You don't want to run it in constant current mode. You want to run it in constant voltage mode. We always want a fixed voltage coming out. That's how most circuits are. There are some circuits where we need constant current, meaning we want the current, we don't want the current to change at all. We want it to remain flat. Most likely like audio circuits, audio amplifiers, transistor amplifiers, those kind of circuits, we want to run in constant current mode. Okay. So as an example, let's say you have a voltage source that's sending out 10 volts, right? Out its two terminals. And you connect a resistor. You connect a resistor of 1 ohm. Connect a resistor of 1 ohm. So what's the current flowing through that power supply? What current is outputting from the power supply? Along with 10 volts, it has to send out some current. Apply Ohm's law, 10 ohms. I mean, sorry, 10 amps, right? So apply Ohm's law, you get I is 10 amps. V is equal to IR. I is V divided by R, so 10 amps. Now, if you connect 10 ohms, the current is 1 amp, right? Voltage remains fixed, current changes. Does that make sense? So it's a voltage source, a constant voltage mode. We change this to 100. And the same thing, I would now be 0.1 amps. So the power supply, the voltage supply will vary the current. It will change the current depending on what the load requires. Okay, depending on what the load requires. And so constant voltage mode or a voltage source. Current source is exactly the opposite, but the same example works. If you have a current source that is supplying, let's say, let's keep it simple, 1 amp. 1 amp, and you have 1 ohm resistance. The voltage being sent from the output terminals is now 1 volt, right? V equals IR, so 1 volt. So V is 1 volt. If you have 10 ohms, V is now 10 volts. Ah, what happened? And it's 100 ohms. V is now 100. Current remains constant. Voltage is varied or voltage changes. So the current source will change the voltage at its output terminals, but it'll keep the current constant no matter what the load value is. Now, of course, there are some constraints in real life, right? So real life power supply, especially like, again, I'll go back to the example of EE251. If you are taking EE251, you look at the power supply and it'll say 25 volts and 3 amps. So it can supply a maximum voltage of 25 volts and or supply a maximum of 3 amps. Cannot go more than that. So even if if I connect 10 ohms to my power supply, it can send 1 amp, no problem. If I connect 1 ohm and I want 10 volts out from it, it needs 10 amps to provide 10 volts. But if it can only supply a maximum of 3 amps, what is my voltage now? How much would my voltage be? 3 volts. So the power supply will not be able to give more than 3 volts. And you can test it out for yourself if you have an actual power supply with you, right? You can connect a low resistance to your voltage source and you try to get like a higher current, it would not go beyond that. That's why we have current limit settings also in there. So if we want to protect our circuit, we do not want it to blow out, we would set a current limit or a voltage limit on there. So all experiments that you do, it'll say set the current limit to like half an amp, like 500 milliamps. That's to protect the power supply and also to protect the circuitry itself. Okay, but that's the definition of a voltage source and a current source. Okay, all right, let's take a 10-second pause, think over it, let me know if you have any questions. Any questions at all? Yeah. If you keep the current constant, then I mean, again, a battery is a voltage and a current source also. It's just technically when we're performing circuit analysis, if you have a constant current coming from that cell, then it's a constant, then it's a current source. There is, oh no, there are batteries which you can buy, which will provide you a constant current. There are batteries that you can buy. There are some rechargeable batteries. And I didn't know this. Apparently now you can buy AA and AA battery cells with a built-in charger. Have you all seen that? I had never seen it until a few months ago. There's a micro USB port inside the AA battery itself. So all you have to do is connect your regular USB charger, micro USB to that, and it just charges. It wasn't that expensive either, like $20 for a pack of 4. Lithium-ion rechargeable. The reason I'm mentioning that is because I read the technical description of that, and it said it would provide constant voltage and constant current no matter how low the level goes. So it would provide constant current for a very long time. Yes. Yes. Well, this is not parallel. I mean, this was just, that's why I have the dotted lines in there. This is like, if I connect the 1 ohm, I get 1 volt. If I connect the 10 ohm to the current source, I know it looks like a parallel circuit, but it's not parallel right now. It's just individual examples. Yeah. All right. Any other questions? Okay. So these sources, whether it's a battery, like as you said, a real life example for a source is a battery. Now, if your battery is rechargeable, then it's both a source and a load, right? So you take your mobile devices, your tablet devices, you put it to charge, like my laptop screen is being charged right now. I mean, not screen, but the laptop is being charged right now. It's running off of the power supply, right? So the battery is being charged, so it's acting like a source. I'm sorry, it's acting like a load because it's receiving the energy. If I remove the charging adapter, now the computer is running off the internal battery. So now the battery is acting like a source. That makes sense to everyone, right? So you can act as both a source and a load, and it's back to charging. Anyway, so a rechargeable battery, all your mobile devices, laptop batteries, smartphone batteries, tablet batteries, they can act as a source and a load, depending on whether it's being charged or discharged, right? Now, the batteries and the power supplies, if you have a 1.5 volt battery, it will supply 1.5 volt irrespective of anything else in the circuit, right? It's supposed to. So it does not depend on its value on anything else. It is self-contained. Okay, it's self-contained. So the sources that we just talked about, they are all independent. They're independent of everything else in the circuit. And so they are referred to as independent sources. So the circular symbol that we saw, the circle that we saw, it signifies that it is an independent source. Independent source. There's a concept in electrical engineering of dependent sources. Okay, dependent sources. Oh, missed an N. Dependent source. And it is the symbol for a dependent source is a diamond. Like this. Now, we won't do problems based on dependent sources, but this is a concept that students should be familiar with. So I do go over it in my classes. If students do want to study it a little bit further, then the extra credit tutorials in homework 5 will cover dependent sources also. So again, it's within the bounds of the classroom, the 15-minute lecture time, there's not enough time to like cover everything, right? Again, EE201, non-EE majors, we're just skimming the surface, you're snorkeling. We don't go scuba diving. Like what you learn in one quarter, the EE major will learn like over the period of one academic year. Okay, so we don't go too in depth. So dependent sources, again, it's a concept that I like to bring up in class so students are familiar with the concept. But if you want to do any kind of problems or anything, then it's like outside the bounds of the classroom. You can do it for like extra credit and stuff. A dependent source, again, can be of both kinds. It can be voltage as well as current. So if you have a dependent source that supplies constant voltage, it's a dependent voltage source. And if you have a dependent source that supplies constant current, dependent current source. These are not actual acronyms. I just came up with these acronyms in the previous class. The DVS and DCS is just something I'm using right now. Dependent voltage source and dependent current source. Based on the dependency could be on voltage or current, or current, right? So you could have a voltage source that depends on a voltage on some other part of the circuit. Okay, and again, complex, the examples for this would be complex, like a circuit, like a complex circuit in there. So we won't get into that. But suffice to say, you have a 2x2 matrix. You have a voltage source that is dependent on a voltage. So we say that it is being controlled by that voltage. So we have a voltage controlled voltage source. We can have a current controlled voltage source. We can have a voltage controlled current source, and we can have a current controlled current source. So you can have 4 types of dependent sources. Does that make sense? Right? You have a voltage dependent voltage source, dependent current source, and each one of those could be dependent on a voltage or a current. One quick example I always like to point out, and this would be, well, I'll let you tell me what kind of dependent source this is. So let's say this is Vs somewhere here, this is ground, you're applying a voltage between these 2 points, and we obtain V out in the middle of the circuit. Now, depending on what the designers choose, again, voltage divider is something that we'll look at, but depending on the values of these resistances, V out will be a fraction of Vs. Okay, V out will be a fraction of Vs. That fraction could be anything, depending on the values of the resistances. But for now, as an example, let's say that it is 50% of Vs. So what kind of source is this? The output is voltage, and the dependency is also voltage. So it's voltage controlled voltage source, VCVS. So voltage controlled voltage source. But anyway, the point is, if Vs is 10 volts, then V out is going to supply 5 volts. If Vs is 20 volts, V out will supply 10 volts. It'll be constant. It's not going to change. It'll remain constant. As long as Vs remains constant, V out will also remain constant. But the level of V out changes depending on the level of Vs. If Vs is 1 volt, then V out is going to be half a volt. So that's a very quick and easy example of a voltage, dependent voltage source, right? Dependent voltage source. And that's actually what happens in your smartphones, in your laptop adapters. If you've, anyone ever build your own desktop computer? Anyone? Like, so you got Molex connectors and SATA pin connectors, right? So there are multiple voltages on there, 5 volts, 3.3 volts, multiple outputs, right? So power supply has different voltages coming in. Yet, if you connect a laptop adapter, only has one voltage. More likely than not, it's 19 volts DC coming out from most laptop adapters, 19 volts. From 19 volts, you have to generate 5 volts for your USB ports. You have to generate 3.3 volts for your digital logic circuits. You have to generate multiple different kinds of voltages. So from one single value of voltage, you're generating like 5 or 6 different kinds of voltages. That's where you would use something like this. And that would be an example of a dependent voltage source. All the internal circuitry of the laptop or the computer depends on one single voltage, but that voltages are all generated separately from that one single input. All right, questions? Questions? Any questions? Yes.
Can you explain how you determine that it was a voltage controlled voltage source?
Oh, so it's basically just outputting or sending out V out. So we are only concerned with voltage right now. So it's a fixed level of voltage. V out would be like 5 volts, for instance. They will stay at 5 volts constantly. But it depends on its value at some other part of the circuit, which is Vs. And Vs is right there. So V out would be 50% of Vs. If Vs remains at 10 volts, then V out would be 5 volts. If Vs changes to 20 volts, then V out would change to 10 volts. So it will remain constant. So it's a voltage source, but it's dependent on Vs. And hence it would be a voltage control voltage source or dependent voltage source. Sorry? V out is not, well, larger picture, yes, they're variable, but as long as, so if you take the example of the laptop adapter, right? So Vs would remain at 19 volts. That's not going to change, right? So then V out, if we design V out to give out 5 volts based on that fraction, then V out would remain at 5 volts. It's not going to change. Now, if you, instead of 19 volts, you plug in like, I don't know, 50 volts in your laptop, technically, if the circuits are able to handle it, then V out will scale at the same level. Does that make sense? I mean, before it scales out, laptop, that adapter, laptop might blow out the power board. But theoretically, if the components are able to handle it, then V out, if Vs increases, V out would increase at the same level. It will scale at the same level. Right? Make sense to everyone? Yeah. So again, we will not solve problems on dependent sources. I believe there's not enough time for students to grasp the concept. I mean, 10 weeks is just not enough time to like do so many things. So, but students should still be familiar with the concept of dependent and independent sources. So most of our circuit analysis will exclusively deal with independent sources, circulars. Yes.
Will 321 cover dependent sources?
No, we only cover it here. There are some circuits, I don't know if they use, it's certainly possible that in 321, they might want you to use like some dependent source, but I have not seen any instructors do that. When I taught 321, we were semiconductor devices. So we're talking about PN junction diodes, transistors, op amps, semiconductor devices. Oh, one thing I would like to point out is that 321 is a direct continuation of 201. Okay, so in a semester-based system where we have 14 weeks, I used to teach this many years ago in a different university, semester-based system. The students there will learn 201, and they will learn a certain portion of 321. So If it fits into your schedule or your tech electives or something, and you have the interest, I would strongly recommend that you take E 321. It's a direct continuation of 201, but it's kind of like separate. So you would use circuit analysis techniques in 321, but you learn about semiconductors in there. All right, let's see. Oh, one final concept that I want to talk about was node voltages and node voltage in a circuit. And so I'm going to use a 2D illustration. It's kind of like a graph, and it deals with 5 points in a circuit. Okay, 5 points in a circuit. So the illustration will make much more sense than my words. This is ground level. Let's say it's the x-axis, okay? 0 volts. And we have 5 points in the circuit. We don't know where they're connected. We don't care how they're connected or what they're doing. All we know is 5. It's point A right here, point B right here, point C right there, and point D right here. X-axis does not matter as much as the y-axis, the levels. Okay, so what I'm trying to get students to understand is looking at the levels of voltages. And then there's point E, all by itself, lonely down at the bottom. All right, and I'm going to tell you that D is 1 volt, C is about 3 volts higher than ground, and A and B are 5 volts. E is below ground, 2 volts below ground. So technically it would be minus 2 volts. I'm going to put down 2 volts anyway. Okay. Does the illustration make sense? You have different points in the circuit, different nodes in the circuit, A, B, C, D, E. They're all at different voltages. The voltages are all with respect to ground. So if I ask you, what is the voltage at VD? Single subscript notation. Single subscript notation means voltage at D measured with respect to ground, right? D, voltage at D measured with respect to ground. And so that would simply be 1 volt, right? 1 volt. So VD is 1 volt. How about VCD? 2 subscript notation. First subscript is the point of measurement. Second point is the point of reference. So VCD is voltage at C measured with respect or with reference to D. So it's VC minus VD, right? VC minus VD. Again, voltage is nothing but the difference in potential between 2 points, right? That's what I'm trying to illustrate with this. So it's VC minus VD. And VC minus VD is what? 2 volts. Easy to see with this illustration, right? 2 volts. How about VAB? 0. So it's VA minus VB. So it's 5 minus 5, 0 volts. How about VE? Voltage measured at E with reference to ground. So positive reference is here, negative is here. So it flips. And so you get minus 2 volts. Minus 2 volts. If you measure the voltage at ground with your reference point at E, then what do you get? Plus 2 volts. So even though you're measuring at ground, your reference point is crucial. And it's easy to see with this illustration. Yes.
Wouldn't that be 0 volts minus 2 volts if it's measuring at ground? If you're doing like E ground minus EE.
So it'd be 0. Oh, yeah, I see what you're saying. No, but E is below ground, so it's minus 2 volts over there.
Like the magnitude.
That's just the magnitude I wrote. Yeah, that's just the magnitude. And that's exactly why I like to use this illustration, because it's easy to see a different level. So you have 0 here, and this is 2 volts below. So it's, -2. It's below ground level. It's below 0 level. And then there is, oh, did it finally stop working on me? It's recognizing. Is it not working? Okay. It's just a few more minutes. Still not responding. And then VED. So VDE is plus 3 volts. VED, positive reference here, negative here. This is below 3 volts below D. So it's minus 3 volts. So VED is plus 3 volts. VED is minus 3 volts. Okay. VED is minus 3 volts. Let me see if I can troubleshoot this. Still not responding. Oh, that wasn't my device. Hopefully. Oh boy. Anyway, for chapter 1, these are the concepts that I wanted to talk about. There was, yes, question? No, VDE is plus 3 and VED is minus 3. Yeah, because you're looking at it from above, if that makes sense. And respond to everything else. Let's see. Let me pause. Okay, so before we were interrupted, we were talking about VDE and VED. So I'll make those notes. VDE is VD minus VE. That gives us 3 volts. And VED is VE minus VD. Gives us minus 3 volts. All right. Now, there was one more thing. Remember how I said current always goes from high to low, right? Current always goes from high to low. So current is like any other physical quantity. If you have 2 points in a circuit, or let's take a resistor for instance, 2 ends of the resistors, if they're the exact same voltage, there's no current flowing between the 2 points, right? There's no current flowing to the resistor. If one point is higher than the other one, then current would flow, and the current is flowing from higher to lower. It's like any other physical quantity, like temperature, like pressure. Temperature always goes from high to low, pressure always goes from high to low. So current always goes from high to low. All components except a source. So if you have a resistor, a capacitor, or an inductor, it'll always go from high to low, from plus to minus. So if you have a resistor, high to low. So you have a resistor, and if you are given the polarity plus and minus, then the current is flowing from left to right. Okay, makes sense? Current's going from left to right, plus to minus. Conversely, If you are given the current direction, you're given the current direction, then based on the direction of the current, you can write that the point of entry is plus and the point of exit is minus. So if current direction is given, let's take left to right in this case, then where is the plus sign, on the left or the right? On the right, right? Point of entry is plus, point of exit is minus. And this is true for all passive components, whether it's resistors, capacitors, or inductors. Point of entry will be plus, point of exit is minus. For a source, however, it's the exact opposite. Again, remember, you have to balance it out. Source is supplying the energy, so the current's flowing in the opposite direction for a source. Well, opposite in the sense that it's going from minus to plus. And so if you have a source, if you have a voltage source, then the current is going from minus to plus. If you have a current source, then you could say plus and minus right there, following the same rules. So for a source, it goes from low to high. It's opposite of resistors. And for a voltage source, if the polarity is given for a voltage source, then the arrow, it goes from minus to plus. For a current source, the minus would be at the tail end of the arrow. Yes.
One about the source, if the magnitude of the current is negative, does that affect it, or would it?
No, so that would just be a representation. So the magnitude doesn't change, the sign would change. So if I take the arrow and I flip it, all I would get is a minus sign in front of it, but the magnitude would remain the same. So if it's 5 milliamps current going to that resistor, so the question being asked is, if we flip the arrow, then does it change the sign? So the sign would change, but the magnitude remains the same. Does that answer your question?
Because if it's negative, it would go in the minus.
No, again, that would just be a representation. So if the voltage polarity is given that way, plus minus, then our assumption would be that the current is flowing from left to right. Yeah. Now, when we solve circuits, remember I said we assign voltage polarities and current directions randomly, right? So let's look at an example for that. So if you have a circuit that looks like this, now we are given the voltage source, let's say, we would be given like a value, or for like a notation for the voltage source, just Vs. Values for the resistors would be given, and you'd be asked to find the voltages and the currents for the rest of the circuit. So again, remember, when we first start analyzing circuits, we randomly assign the polarities for the voltages and randomly assign directions for the currents. But those assumptions are based on logic, right? So the logic here is that if Vs is given as plus up top and minus at the bottom, which direction do you choose for the current? Up, up or down? Up, right? So it's going up. So it's going from minus to plus. So current goes from minus to plus. Make sense to everyone, right? Now, you're driving around, you start driving from this point, there's only one pathway to take. Gonna go up there, make a right turn, so to speak, right? So it's gonna go through the resistor this way. Once it goes to the resistor, you hit the node or the junction, it's going to split. When it splits in two, some of it's gonna go down here, some of it's gonna go to the right. This is going to follow this pathway, right here, join up again, and complete the circle, right? So those are the logically assumed directions for the currents. Now, based on the directions of the currents, we can apply voltage polarities to all of these, right? Point of entry is plus, point of exit is minus, so it goes plus, minus, plus, minus, plus, minus, and plus, minus. That's how we make the assumptions. So we assign it randomly, we assign it arbitrarily, but those assumptions are based on logic, and that is based on fact, right? So it's going from the source all the way to the resistor, going all the way around to the circuit. So all points of entry are plus, minus, plus, minus, plus, minus, and so on and so forth. Yes.
So for example, if it was given that the second resistor on the top, the value was -5, then you put the arrow.
If the current was given, you mean?
Then you would flip the arrow.
Yes. Yes. Yeah. Yep. Absolutely. So the question being asked was if the current direction was the current value was already given, then how would we take it? So if the current value was given as -5, then we would take the arrow to be opposite of what is being shown, right? The value what is being shown, and that's all it means. The sign of a voltage or of a current when it's negative, that's all it means. So you could choose the current to go in the opposite direction instead of going down like this. So we are choosing the current to go like this, right? You could choose it going the opposite direction this way. It would not make any difference in your analysis, or not at least the analysis. It would not make any difference in your final answer. Your final answer will always be correct. And the reason is when you portray your final answer, it's not just by itself. You have the number in there. So voltage or a current would have either +5 or -5. The plus simply states that whatever assumption we made is correct. The minus simply means, well, let me not use the word correct. Let me use the word, the plus sign indicates that the assumed direction at the beginning of the problem matches up with my final answer. If it's minus, if I choose this and obtain minus, it just means that the current is flowing in the opposite direction. That's all. But this opposite direction, along with the minus answer, minus sign, is a valid answer. You will still get full points for that answer. Does that make sense? If you choose this and you get -5, then it's incorrect. But if it's this and minus, then it's technically the same as +5 and the arrow. So you would still get the full points. And so that's why I say, it doesn't matter what you choose, as long as you're consistent within the problem, you will get the correct answer at the end. But your answer has to match up with the assumed direction at the beginning of the problem. Okay. All right. So any questions about that? That makes sense? One other point. A student in the previous section brought it up. It's an excellent question. So I think I should speak about that. What they asked was, you have a minus sign here, you have a plus sign here, and you have a plus sign here. Yet, technically, this is all the same node, right? That T in the middle, up top right here, the T junction is the exact same node. So electrically speaking, it has the same voltage, it has the same potential, right? So how do we have different signs up there? Why do we have a minus and a plus and a plus? Yes.
In relation to the other side of it.
Exactly. That's the perfect answer. So the minus sign that we see here, let's zoom into it a little bit. So this minus sign is only with respect to this point right there. And this plus sign is only with respect to this point on this side. For all other reasons, for all the references, this node is exactly the same, right? Does not make any difference. It's exactly the same. So there's a minus and a plus in there, but again, it's a reference point. That minus is lower only with reference to the plus sign on the left, not with anything else in the circuit. And that's why you have a minus and a plus in there. So I still have a couple of minutes, but I'm going to say that this chapter is over. Chapter 2, we'll begin with resistive circuit analysis. Again, this is kind of like a refresher because students would have done this in physics, series connections and parallel connections, right? Series connection of resistors. So I do want to point out, don't be in a rush. Still have 2 minutes. When you have two or more components connected together, as long as they are connected by one junction, they are said to be in series. So if this is component 1 and 2, these are points A, B, and C. As long as you only have two connections at B, then the outer two connections, we can say that 1 and 2 are in series. If you have more than two connections, then they are no longer in series. So you could have a third component right here called 3, and 1 and 2 are in series, and 2 and 3 are also in series. So we can say 1, 2, and 3 are all in series between A and D. If you have more than one connection at points B and C, then they are no longer in series. A real life example of this would be the string lights that we use for like Christmas, for festivals. They're all connected in series. Oh, that should be a light bulb. And then you plug these connection of string lights all into your power outlet, 120 volts, and all of them go on. If there's a break anywhere in the circuit, light bulb fails, then the entire circuit fails because there's no pathway for the current to flow through. All right, we'll pick up here again on Friday. If you have any questions, I'll be in my office until 3 o'clock. Send me an email. I can meet you via Zoom or I'll be happy to see you in my office.